Welcome to section 6.2 of the textbook, where we are going to look at the modulus of a complex number. Right, so in this section we will give a geometric interpretation of complex numbers, and we are also going to identify each complex number z, which is equal to a plus bi, with the point AB in the plane, where a is the measure along the horizontal axis, which is called the real axis, and b along the vertical axis, which is called the imaginary axis. And the resulting plane that we get from that is the complex plane, or the Argan plane. And the name Argan plane comes from the mathematician Jean Argan. So in the figure below, the complex numbers x is equal to minus 3 plus 2i, z, which is equal to minus 1 minus 2i, w, which is equal to 2 plus I, and the conjugate of w, and the conjugate of w plus, the conjugate of z plus w are plotted. And so we have our horizontal axis, which is called the real axis and denoted by RE. And then we've got our vertical axis denoted by IM, representing the imaginary axis, right? And so for x, we have got minus 3 plus 2i. So in the real axis, we say minus 3. In the imaginary axis, we say 2. So minus 3 to the left, and then 2 upwards, we get our x. And for z, we will say minus 1 to the left, and then minus 1 down, we get our z there. And for w, we say 2 to the right, and then 1 up, we get our w there. And then if we want to find the conjugate of w, we have 2 minus I, which is 2 down, 2 to the right, and then minus 1 down, which is there. And this was just a reflection of w, as you can see, in the real axis. And then for lastly, for z plus the conjugate of z plus w, if we do the calculation of the conjugate of z plus w, we get that it is equal to 1 minus I. And so we go 1 unit to the right, and then minus and then 1 unit down, and then we get the complex number there. Right, and just a bit of motivation on the modulus of a complex number. So if we think of the absolute value of a real number, it is interpreted as the distance between the point on the line corresponding to A and the point corresponding to 0. So if you remember that, suppose we've got this as a line here, and then we want to get the modulus of 3, we would have said the distance between the point here 3 and 0. Or if we do it from that side, suppose we want to find the modulus of minus 3, we would have said the point minus 3 to 0, which will give us 3. So the distance will be 3. And so the modulus of a complex number becomes a generalization of this notion of an absolute value of a real number, and it has a similar geometric interpretation, as we shall see. So the modulus of a complex number z, which is equal to a plus bi, is the real number, the square root of a squared plus b squared. And just as an example, example 6.2.2 in the textbook, suppose we've got z, which is equal to 2 minus 3i. Then the modulus of z will be equal to the square root of 2 squared plus minus 3 squared, which is 2 squared plus 3 squared, so which is equal to 13 inside. So the modulus is the square root of 13. And so the modulus of z, which is equal to a plus bi, may be interpreted as the distance between z and the complex number 0 in the Argan plane. And this is what the figure here is showing us, that if you've got a complex number z, then its modulus is the distance between z and 0, which is that, right? And then in general, if you've got two complex numbers z and w, then the modulus of the difference of these two complex numbers may be interpreted as the distance between the two complex the distance between the two complex numbers in the complex plane. And we expect the modulus will also satisfy properties that are satisfied by absolute values, right? So that is our theorem 6.2.3. So let z and w be complex numbers, then the following statements are true. So the first one tells us that the modulus of z is greater or equal to 0, and the modulus of z is equal to 0 if and only if z is equal to 0. We know that this property is satisfied by real numbers, and the real part of z is less than the modulus of z, and also the imaginary part is less than or equal to the modulus of z. And the modulus of z is equal to z times its conjugate. And also number 4 says the modulus of the product of z and w is equal to the modulus of z times the modulus of w. And number 5 says the modulus of the conjugate of z is equal to the modulus of z. And for 6 we have, if w is not a 0 complex number, then the modulus of its inverse is equal to 1 over the modulus of w. And if w is not equal to 0, then the modulus of z over w is just the modulus of z over the modulus of w. And then lastly, we have got the triangle inequality, number 8. The modulus of z plus w is less than or equal to the modulus of z plus the modulus of w. So we're going to look at proof of 1 and the proof of 8, and then the remaining will be left as exercises. So let z be equal to a plus bi. So we want to prove this statement. Then by definition, we know that the modulus of z is equal to the square root of a squared plus b squared, which is greater or equal to 0. And so that the first part is true by definition. Now let's look at the second part. So firstly we are going to go that direction. So suppose z is equal to 0. Then what it means is the modulus of z is less than or equal to 0 squared plus 0 squared, because z, which is equal to 0, can be written as 0 plus 0i. So therefore the modulus becomes that which is equal to 0. So the first part is done, going that direction. And then going this direction, so suppose z, the modulus of z is equal to 0. Then what we know is if we square the modulus of z, we get a squared plus b squared, and this is coming from the definition of the modulus, and we know that that is equal to 0. But we know that if a squared is greater or equal to 0 and b squared is greater or equal to 0, this we know, this is a property of real numbers. And so it means that if we add these two and they are greater or equal to 0, both of them, and if we add them and we get a 0, it means that a squared was 0 and b squared was also 0. And so therefore if a squared is 0, a is equal to 0. If b squared is 0, b is equal to 0. And so therefore the z is equal to 0 plus 0i, which is the which is the zero complex number. And so we have arrived at the conclusion here. So that concludes the proof of 1. Now let's look at the proof of 8, the triangle inequality. So we know that according to property 3 in the theorem, so property 3 tells us that the modulus of z is equal to z times its conjugate. So if we take the modulus of z plus w squared, we then get that. And then it follows that from theorem 6.1.12 that if we have that it's supposed to be squared here, which is equal to that, then we can do an expansion of this, which leads to z times its conjugate plus z times the conjugate of w plus w times the conjugate of z plus w times its conjugate. And then we can then, so that one z times its conjugate is equal to modulus of z squared, and then w times its conjugate is equal to the modulus of w squared. Now so if we look at theorem 6.1.12 part 3 and 4, we will see that the modulus of w times sorry, not the modulus, w times the conjugate of z will be equal to the conjugate of w times z. And so therefore we also know, and this is given as an exercise to show that if you take z times its conjugate plus the conjugate of z times its conjugate, you're going to get 2 times the real part of z times its conjugate. And from here we know that this can be rewritten as that, right? And so therefore so basically what we have is this part is equal to 2 times the real part of z times its conjugate times the conjugate of w. Now by properties 2, 4 and 5 of this theorem, so 2, 4 and 5, we can move from this is equal to 2 times the real part of that, but we know that the real part of the real part of a complex number is less than its modulus, so we can then move from that to that is less than or equal to 2 times the modulus of z times its conjugate, which is equal to 2 times the modulus of z times the modulus of w. And so therefore what we have shown is that if we take this squared is less than or equal to the modulus of z squared plus this, which replaces that, and then plus the the modulus of w squared, which if we do a factorization, we will find out that this is just equal to the modulus of z plus the modulus of w all squared. Now because we know that the modulus of z plus w is always greater or equal to 0, and also this always greater or equal to 0, the sum of these two complex, sorry, the sum of the modulus of these two complex numbers is greater or equal to 0. And this is coming from property 1 of this theorem. It follows that if we take the square roots, we are going to get that is less than or equal to the modulus of z plus the modulus of w. So note that this is supposed to be squared there, this is supposed to be squared there, right? So that then concludes our proof for the triangle inequality. And so the rest of the proofs are, as we mentioned earlier, are given as exercises, and the exercises are exercise 6.2, numbers 5 to 8. Thank you.